All right, you all, I'm back, ready to do some more linear algebra problems. I think I shall continue from where we were um, uh, before, starting with what, D of this problem. So A is there, B is find the distance with the line, projection. Um, this is C. Right? This is C, the easier way of doing C. And B starts here. Right? So D says find the distance from point W to the plane by using projection, right? So find the distance from, so why don't we draw the vector again, the vectors of the plane, the Cartesian plane, and we have a plane up here somewhere, and we know this line that's coming straight from the origin to the line. We know there's XO somewhere, and XO is on the plane somewhere. And now we have W, which is, we'll put W here. We'll call this W. And we want this distance, all right, using projection. So we know this point is on the plane. We know this point is on the plane. So uh, we know L, we know XO, both of them are on the plane. So we can actually pick either of these to work with. Um, Probably XO would be easiest. So remember, right, the line is a kind of fraction. I don't want to deal with that. So let's go to XO, which was negative 200. Oh, I realize I skipped the page. So this is XO. And what we can say is that if we connect a line here, then we can use this line to get our distance to the plane. So how does W and A or W and XO work with each other? So W plus XO will be out here somewhere, but W minus XO should be that. So we'll make a point this way. technically that'll be XO minus W. So XO minus W would go like this, which I'll call what? P. And that's the projection we'll work with. So the projection of PO the projection onto, what would that be? A projection onto? I guess that would have to be the projection onto A, because this line here is in the same direction as the normal vector. It's just scaled differently. So that's going to be A. So the projection uh, onto A of P equals some scalar of A. So alpha equals projection onto A of P divided by A. And then we could use the other projection thing, which says that A dot P equals, so P is doing the projecting, so it's A dot the P that's parallel to A plus the P that's perpendicular to A. So that's going to be A dot P parallel plus A dot P perpendicular. So what I can do here is the same thing we did earlier. The one that's perpendicular to A will be 0. So we know we have A dot some scalar of A. These times some scalar of A. So that's scalar magnitude of A squared. So that means that alpha equals A dot P over magnitude of A squared. All right. Easy enough. So the projection of P onto A equals A dot P over magnitude of A squared times A. And they want us to find the distance to W from the plane, and that's what that is, with the projection of P onto A. So all I have to do is, they want the distance, so they want the magnitude. So it's the magnitude of this. So A dot P equals, so first we need to figure out what P is. So let's take this step by step. So P equals XO minus WO equals P equals XO minus WO. So that equals XO is negative 200 minus WO. They gave us WO. WO equals 3, negative 3, negative 5. All right. 3, -3, -5. So that equals -5, 3, 5. So that's our P. So now A dot P equals, and we know what A is from earlier, 2, -3, -6. Dot product, -5, 3, 5. So that equals -10 minus 15 plus 30. So that equals 5. I'm curious what would happen if the numbers on my vector were opposite. I would have a +10. Oh, and it's 9. I'm overlooking some numbers. I have +10. I'd have +9 and 25. No, +10, +5, and +10, +9, and +30. Right? So I see what's going on here. I left off a negative. So we have -10, -9, and -30. If my normal was going in the opposite direction, we'd have +10, +9, and +30. Either way it goes, it gives us the same magnitude of an answer, which is -49, negative or +49. And the magnitude of A squared, that's going to be 2 squared plus 3 squared plus 6 squared. So that equals 4 plus 9 plus 36. So that's 49. And the magnitude of A equals 7. So putting that together for the magnitude of that projection, we have the magnitude of all of that. So it's 49 over 49 times 7 equals 7. I remember, let me see. Yep, it equals 7. So that's correct. So now the next question is saying, find the point on the plane closest to W by using a parametric equation of the line through W with direction vector A. Okay, so we're going to copy this same drawing. And we can say that and we can say that we know that this direction here is the normal direction, this line right here. So we know that the direction from the plane to W is some scalar of A. We're just trying to figure out what that scalar is. Also, I think we can do this the same way as the last one. So that line equals scalar A, which equals the scalar A1, A2, A3, or actually let me call that X. No, it's better to keep it A. So that equals alpha A1, alpha A2, alpha A3. So that means that this is an X1, X2, X3, right? And the plane is still the same plane. That's going to be there it is here. It's going to be this. Copy, I think it is. So since this is the plane and the line is going to be some point on the plane from W, actually we can call this some scalar of W. So this is going to be 2 scalar W1 minus 3 scalar W2 minus 6 scalar W3 equals -4. And we know what W is from earlier. I'll copy that down. So we have 2 alpha 3 minus 3 alpha -3 minus 6 alpha -5 equals -4. So 6 alpha plus 9 alpha plus 30 alpha equals -4. So 45 alpha equals -4. So alpha equals -4 over 45. So that means the point is going to be this plugging in alpha. So L equals some scalar alpha. And I want the distance the closest point on the plane. That's going to be negative 4 over 45, 3, negative 3, negative 5. So that equals negative 12 over 45, 12 over 45, 20 over 45. Right, and let's check the magnitude on that. So that's the square root of each of these squared summed together. So that's going to equal this in my calculator. Right, so that's not, oh, hold up. Yeah, that's not correct. Right, so let's see what happened here. I believe the modality is correct. L is some alpha A, but it's also some alpha W, which is the line. Perhaps what I'm missing is we're starting at that point. So the line is actually that alpha plus W. So W is the starting point, and then it's scaling some distance along the vector. So I think that's what I missed. Plus W, plus W. So this would actually be plus W. Let me erase this. Would it be easier just to, let me just redo that part. Right? So we have L equals alpha A1 plus omega 1 plus alpha A2 plus omega 2 plus alpha A3 plus at least W3. And what we can do is simplify this so that this is X, this is Y, and this is Z. So that means the plane would be, and do I have that copied? No. It's still our plane. So that means it's going to equal 2 alpha A1 plus omega 1 minus 3 alpha A2 plus omega 2 minus 6 alpha A3 plus omega 3 or W3. So what that's going to be is big long mess. So that's 2 alpha A plus 2 omega 1 minus 3 alpha A2 minus 3 omega or W2 minus 6 alpha A3 minus 6 omega 3 equals -4. And I know what my W is. So that's going to be alpha 2A. Oh, and I know what my A is as well. So this is looking more promising. Have to remember that the line is scaling from W in the direction of vector, the normal vector. And so basically our W is our PO, our XO, our originating point. And we just scale from there. So what I had before was just a direction, but not a starting point really. And technically it wasn't a direction of W, so it wasn't the direction of the normal. So I have to remember that you start at the starting point and and move in the direction of the normal vector. So that's what we moving in relation to. So this will be alpha 4 plus 6 minus alpha 9 plus 9 minus alpha 36 plus 30 equals -4. So now I have -45, -41 alpha plus 45 equals -4. So -41 alpha equals -49. Alpha equals 49 over 41. So now we can go back and figure out what the line is, what the point on the plane is, since we're scaling from W to the plane. So this should give us the point on the plane. I should have factored in, or maybe I couldn't factor in W sooner. This is going to be 49 over 41, 2, -3, -6, plus 3, -3, -5. So that equals, I wonder if I can do this all with my calculator. Let's see. Nope, it can't, unless I'm just not sure how to add vectors on the calculator. Seems like it's complicated or sophisticated enough where it should be able to do it. I'll try one more thing. I'll try to input them as matrices and see if that allows me to do it. on the truth. Let's see if I can add these matrices. And I can. So let's see if I can change this to a fraction. All right. So we have 221 over 41, negative 270 over 41, and negative 499 over 41 is the point, a very odd point. Let's get the magnitude of this point. Nope. Let's see what I missed. All right, I'll look at what I did last time and see what detail I'm missing. Right? We're doing the last problem of 8. So it looks like, for the most part, I did everything the same. So I still had this 12 plus 6. Ah, this is what I did. I left off a negative. So this should be 4 alpha plus 6. And this is a negative in front. And alpha 2 is negative, so that's a positive 9. And I did the same thing on the last one. That's a negative 6. So this would be positive. And right, so I left off those negatives. So then we have 45, 49 alpha. And that's still 45. So this would be 49. So this will be 1. And this will be positive. I have to put the positive back. All of those are positive. All of those are positive. So it's actually negative 1. All right, so that was the issue. So this would be negative 1, not that. So then we would have 1, negative 9, negative 30. And we know the magnitude of that I don't know what that's going to be. Let me make sure I didn't miss another number. I multiply those. So this will be 1. Let me back up on this part. So the line, when I did it last time, I did W minus B. It should still be W plus TA. Okay, I see. This is the line. Now I know what alpha is, -1. These are vectors. Remember that these are vectors. So x1 equals -1, 2 plus 2 equals 0. It's supposed to be a 3. Yep, yep, yep. It's supposed to be a 3. It is equal to 1. x2 equals -1, -3, -3. So that is 0. And x3 equals -1, -6, -5 equals 1. So this is the line, the point on the plane. So in other words, L equals, you're starting from W, plus you're scaling directly to the plane, and this equals this point on the plane. That's the point on the plane. So the distance from W to the plane is the difference from W to L. So that equals L minus W. So that equals 1, 0, 1 minus, I'll copy this down, right? So that equals -2, -3, 4, nope, 6. It becomes positive. And the magnitude of that is +3. So that's the vector going from W to L. That's that vector there. and this now becomes L. So the magnitude of that is 4 plus 9 plus 36 equals square root of 49 equals 7. So the magnitude of WL does match the magnitude from that we had before from W to the plane, but now we did it as a line. So you have to remember that the line itself is just a the scale normal vector from W plugging in the values into the X of all the values of that line. Remembering that these are vectors gives us the X, Y, and Z coordinates of that point on the line. Then we could use the difference between the point on the line and W to get the vector between them from one to the other. So technically this is if I add this to W, I get L. This is from WL. So I subtract W. So if I add this to W, I get L. Then I take the magnitude of that line and it matches the distance from W to the plane. So that's fine. So why don't we jump to 4.4, at least 1.4. And why don't we do 1.4a? B and D for number 3. Okay, so to 1.4 we go. Number 3. Why don't we do a harder one actually? Let's do G. And we have an answer for G. So I'm going to copy that matrix down, and we need to get the reduced echelon form. So echelon form has any number as the pivots. Reduced echelon form has ones. And then we need the general solution for AX equals 0. So I'll try to remind myself of that one as we go as well. We'll do another number G. So we have 1, -1, 1, 1, 0, 1, 0, 2, 1, 1, 0, 2, 2, 2, 0, -1, 1, -1, 0, -1. So I'll check that. 1, -1, 1, 1, 0, 1, 0, 2, 1, 1, 0, 2, 2, 2, 0, -1, 1, -1, 0, -1. All right. So what I can actually do, many ways to go about this. I'm going to decide to move some tables around, and it's going to add row 4 plus row 1 to row 1, and row 4 plus row 2 to row 2. So this is going to be minus 1 minus 1 plus 1 plus 1 minus 1 minus 1 uh, and minus 1 minus 1 minus 1. So that's going to be, so minus minus plus plus minus minus 0 0 minus minus. So that's 0 0 0 1 negative 1 0 1 1 1 0 0 2 2 2 0 negative 1 1 negative 1 0 negative 1. Now I'm going to so this is a free variable, because if I subtract minus 2 row 2 to row 3, that's going to zero out that whole line. So this is going to be 0 0 all the way. And what's left for me to do is to get rid of most of other things, but it'll all add up more things. So let me multiply this by negative 1. Right? And I'll move some tables around. So I have 1, negative 1, right? So sometimes my application freezes. So let me share with you my links while I fix this. Let me share with you my links while I fix this pad. So be sure to like if you haven't, subscribe if you haven't. Right? So it didn't erase too much. So I'm going to move some things around. And I remember multiplying this times negative 1. So this became positive 1, negative, positive, positive. So now I have 1, negative 1, 1, 0, 1. And then I have, that was this line. And then I have 0, 1, 1, 1, 0, which is this line. Then I have 0, 0, 0, 1, negative 1, this line. And the next line is all zeros. And at this point, it seems like whatever I do, I'm going to add more problems to something. All right, so let me look over this and see if I did something wrong. 1, negative 1, 1, 1, 0, 1, 0, 2, 1, 1, 0, 2, 2, 2, 0, negative 1, 1, negative 1, 0, negative 1. I added 4, well, 4 to each of those. Subtracted the 1, added the 1, subtracted the 1, subtracted the 1. So it became 0, 0, 0, 1, negative 1, 0, 1, 1, already a 1, 0. I subtracted 2 of row 2, if it made it row 3. So that became all zeros. Change that to a positive. So you have that. Positive, negative, positive, 0, positive. And it seems like anything I do at this point would just make things worse. All right, so I'll leave that like that for now. And then it says, and give the general solution of ax equals 0 in standard form. So this equals 0. So that means, naturally, let me go ahead and copy it again. So really it's saying that x1, x2, x3, x4, x5 actually equals 0, because I have to have as many rows as columns on the first one. So that means that x1 minus x2 plus x3 plus x5 equals 0. x2 plus x3 plus x4 equals 0. X4 minus x5 equals 0. So I have to put that into standard form. That would be x1, x2, x3, x4, x5 equals, so let's say x1 equals x2 minus x3 minus x5, x2 equals minus x3 minus x4, and x4 equals x5. So that would be x2 minus x3 minus x5, negative x3 minus x4, x3, x5, and x5. So that equals no x1, no x2. So x3, that would be negative 1, negative 1, 1, 0, 0, plus x4, that's 0, negative 1, 0, 0, 0, plus x5, and that would be negative 1, 0, 0, 1, 1. Right? See what the answer says. 1.4 3G. Oh, maybe I picked the 1.4. All right. So it looks like they almost had it. Looks like they did go ahead and do some things here. So we have got rid of the 1. They put the 2. So it looks like they did add this line. So maybe I left off a 0 or something somewhere. So if I added this up there, this would be 0, this would be 2, this would be 1. And then if I subtracted this line, this would be 0 again, and this would be 2, which is what they have there. And if I subtracted this line, this would be 0, and this would be 1. It's odd that they prefer a 2 than a 1. Now, I see the point is that they was able to get these 2 columns with only pivots. And this column has only a pivot as well. So I guess that's the goal, not necessarily the amount of any given number, but trying to get as many columns with only a pivot as possible. But I'm sure this answer is still right, but it wasn't in reduced echelon form when I set that one up. It's awesome. So I'll take a break. And this is where I was last time, by the way. I'll take a break and I'll be back.